Okay, so this lesson is on comparing two means, and we're going to do confidence intervals and tests. So the sampling distribution of a difference of two means. Let's talk about the shape, the center, and the spread. The shape is all about if it's normal or not. Normal distribution follows a normal curve. If the two individual population distributions are normal, then the sampling distribution of the difference of those distributions is also normal. So if both populations are normal, then the difference is normal. If not, both sample sizes are bigger than 30, then the CLT applies. But both samples have to be bigger than 30. Okay, so there's your shape. The center, the mean of the sampling distribution of X bar of the first sample minus X bar of the second sample is the difference in the means of the populations. The spread, which is the standard deviation. So if we're talking about standard deviation, then you know that the 10% condition must hold true. So the 10% condition must hold true for both samples. The standard deviation is the square root of sigma sub 1 squared over the sample size, sub 1, plus sigma squared of the second sample over the second sample size. And that formula is on your formula sheet. So here's a problem, and it's just going to talk about the shape, center, and spread, okay? Medium or large drink. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27 ounces. Okay, now that 27 is mu, not an X bar, because this is talking about the population. So a mean of 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution with a mean of 17 ounces and a standard deviation of 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled with a large setting and 25 cups filled with a medium setting. Okay, now let's stop right there for just a second. I hope everybody can see that there are two distinct samples. There are even different sample sizes. So one of the key things I want you to be able to distinguish is when is it a two sample and when is it a one sample match pairs. So you can see that I have two different samples. I have a sample of large cups and a sample of medium cups. It says let X bar sub L minus X bar sub M be the difference in the sample mean amount of liquid under the two settings. Describe the sampling distribution. Anytime it wants you to describe a distribution, you need to talk center, shape, spread, and outliers. Well, you don't have enough information to talk about outliers here, but you can talk about the center, shape, and spread. The shape of the sampling distribution of x bar sub L minus x bar sub M is normal, but then you have to say why. Because both population distributions are normal. So watch your terminology, watch your vocabulary. The center, mean, of the sampling distribution. So mu of x bar sub L minus x bar sub M. So the mean of the sampling distribution is the difference of the mean of the population. So mu sub L minus mu sub M, which is 27 minus 17, which is 10 ounces. And make sure you use units of measurement because these are means. And then the spread, so sigma sub x bar sub L minus x bar sub M. So again, the standard deviation of the sampling distribution is, all right, look at the formula on your formula sheet, but they don't have the sub 1 and sub 2. They have sub L and sub M. And then they plug in their numbers. And I want you to take a second and pause the video and type that in. And make sure you can type that in correctly and get 0.205 ounces. Now, please note that we did not check the 10% condition because we are not sampling without replacement from a finite population. Okay, so guys, we're going to do one confidence interval and we're going to do one test. So a confidence interval for, and I don't know why those have hats on them. They should not have hats on them. Confidence interval for mu sub 1 minus mu sub 2. So the title of it is a two sample. Now we're talking about means. So we're not Z's anymore, we're T's. Two sample T interval for the difference of means. You're going to define your parameters. Mu sub 1 is the true mean ounces in large cups at this fast food restaurant. And mu sub 2 is the true mean ounces in medium cups at this fast food restaurant. Conditions, it needs to be random, independent for both sample sizes, and normal. Either both population distributions are normal or the CLT has to apply to both sample sizes. If not, graph the data and look for no outliers and no strong skewness. Okay, now, when you look at a graph, you are looking at two separate graphs. When we did a matched pairs, we put our data into L1, L2, and then subtracted them and put that into L3, and we looked at the graph of L3. That's if it was a matched pairs. But if it's a two sample, I need both samples individually to be normal. So if the populations are not normal and the CLT does not apply, you need to graph both samples individually and show that there are no strong skewness and no outliers. Okay. Statistic is going to be x bar sub 1 minus x bar sub 2 plus or minus t star, and then the standard deviation. So these should be for a confidence interval. This is going to be S sub 1 squared, not sigma. So it's not going to be sigma because, hold on 1 second. Oh. Because remember, when you're finding a confidence interval, you are finding a confidence interval for mu sub 1 minus mu sub 2. And when you find that confidence interval, you're going to say we're 95% confident that the difference between mu sub 1 and mu sub 2 falls within this interval. That's because you don't know what mu sub 1 and mu sub 2 are. And if you don't know who that is, then that also means you don't know who sigma is. So if you don't have the population standard deviation, then you have to use the sample standard deviation. And that's why those are S's instead of sigmas. Okay, so watch your notation. For your T-star, now you have 2 sample sizes. So your degrees of freedom to find your T-star is going to be n minus 1. But remember, you have 2 samples, and they don't necessarily have the same sample sizes. So it's n minus 1 using the smaller of the 2 samples. All right, so let's talk through this problem. Big trees, small trees, short trees, tall trees. The Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of the longleaf pine trees in the northern and the southern halves of the forest compare? To find out, researchers took a random sample of 30 trees from each half, there's my 2 samples, and measured the diameter at breast height, DBH, diameter at breast height, in centimeters. Here are the comparative box plots for the data and the summary statistics. Okay, now guys, make sure you understand. This is north and south. Here's my sample size. So this mean right here is not mu. That is x bar sub n if I want to go for northern, and that's x bar sub s for southern. And this standard deviation is not sigma. That's s sub n, and that's s sub s. Because this is all sample data. So really focus on getting your variables correct. Again, you're just communicating that you understand that this is sample data. Now, I know our sample sizes were 30, so the CLT applies, but they went ahead and gave me a box and whisker. I know this looks somewhat skewed right, but it is not strongly skewed right, so we're going to be okay. All right. Now, the first question says, based on the graph and the numerical summaries, write a few sentences comparing the distributions of the longleaf pine trees in the 2 halves of the forest. Okay, if you're going to compare the distributions, and we did this a long time ago, and we weren't necessarily great at it, but we need to compare center, shape, and spread. And when we do that comparison, we need to use actual data to back up our conclusion. You don't want to ramble, but you want to have information to back up your conclusion. All right, so I'm going to pull this down so you can see our statistics. The distribution of DBH measurements in the northern sample is skewed to the right, while the distribution in the southern sample is skewed to the left. Okay, so I just compared the shape. Okay, now let's talk about center. It appears that the trees in the southern half of the forest have larger diameters. I'm comparing those 2. Have larger diameters. And then I'm going to say why. The mean and the median DBH for the southern sample are both much larger than the corresponding measurements for the center of the northern sample. Furthermore, the box plots show that more than 75% of the southern trees have diameters that are above the northern sample's median. All right, so 75% is going to be all of that. Remember, each whisker holds 25% and the box holds the middle 50. So 75% of the southern diameters are bigger than the median of the northern. Now that sentence isn't necessarily necessary, but it's a great sentence. But you would be fine with comparing the mean and the median to compare the centers. All right, so we've done shape, talked about skewness. We've done center, we talked about the mean and the median. And now we're going to talk about spread. There is more variability in the diameters of the northern longleaf pines, as we can see from the larger range. So I'm looking at the box plot. Larger range, a larger IQR, which is the interquartile range, that's the middle 50%, so that's the size of the box, and standard deviation. So guys, make sure you understand they're using this information and this information to draw their conclusions. So the spread, they used the IQR and the range from the box plot, and they compared the standard deviations, because all of that data backs up their conclusion that there is more variability in the diameters of the northern longleaf pines. And then they said larger range, IQR, and standard deviation, and then I would probably go in here with some data. I don't necessarily know if I would try to get numbers off of the box and whisker, but when you get to standard deviation, I would definitely say 17.5 is greater than 14.26, just to give some data. And I'd probably do that with the mean and the median as well. And then just one brief little sentence: no outliers are present in either sample. So again, this is a great review of, unit 5.3 or 5, I can't remember, but where we talked about comparing distributions. Maybe it was sooner. I think it was unit 2. So center, shape, spread, and outliers. Okay, here we go. Here's the main stage. Construct a 90% confidence interval for the difference in the mean DBH of a longleaf pine for the northern and southern half. All right, so here we go. We are a 2-sample T interval, 90% confidence interval, for the difference of means. I have both of my population parameters, mu sub 1 and mu sub 2. And if you wanted to do mu sub n and mu sub s for northern and southern, that would be just fine. So I defined my mu sub 1 as the true mean. So there's that word. The true mean DBH, again, stating what I'm finding the average of. So don't say the true mean of all trees. You have to say what you're measuring. The true mean DBH, because that's what my data is. It's the, what does D stand for? Diameter. Is that right? Yeah, the diameter. Diameter at breast height of all, there's that word. Some of us are dropping the word all, of all trees in the southern half of the forest. And mu sub 2 is the true mean DBH of all trees in the northern half of the forest. Conditions, yes, they were random samples. Since they were random samples, I need to test my independence. So n sub 1 and n sub 2. And so both of those were 30. So 1/10 of all trees in the southern half and all trees in the northern half. Normal. Now check this out. Even though the box plots look strongly skewed, and you don't even have to use the word strongly there. You could just say that they look skewed. Because both N1 and N2 are greater than 30, the CLT applies, and we can assume that they are normal. Now, you don't have to write all of that but you do need to state that the CLT does apply. But what you are addressing is that you see that the box plots are skewed. However, the CLT applies. So I'm finding a confidence interval. So I write statistic plus or minus critical value times the standard deviation. Throw in my letters. Then I throw in my data. The only piece of information that you don't know yet is this guy. So we come over here to find our critical value. So 90% confidence interval. So I'm going to inverse T 0.05 with degrees of freedom as a 29. And that gives me T star to be plus or minus 1.699. Now, please pause this and type this in and make sure that you can get both those numbers. And then we draw a conclusion. We are 90% confident that our interval captures the true difference, northern minus southern, of mean DBH of the leaves in the two halves of the Wade tract preserve. The mean diameter of the southern trees is between that much larger than the mean of the diameter of the northern trees. Okay, so this extra sentence is just saying, okay, first of all, my interval is all positive, and so that means I'm doing, and I did southern minus northern because the southern was bigger, so I would get positive values. So it's just saying, hey, since it's all positive, then that means that the southern trees, I'm 90% confident that the southern diameter of the trees is going to be larger than the diameter of the northern trees by this much. All right. So now let's talk about a significance test. So you're going to say that this is a 2-sample t-test for the difference of means. You're going to define your parameters. Your null is always going to be that the difference is 0, and your alternate is going to be that it's less than 0, greater than 0, or not equal to 0. You still have to be random, independent, and normal. Then we are doing a test, so we're looking at our test statistic. This is a t-test. So T equals, and then I have all my information in there. This is going to be sigma because we are going to have mothership information, I think. If not, then it's going to be S's. So we'll just read and we'll figure out if we have population information or sample information. So we'll figure out which one we need to use. So let's read. It says, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed the relationship between calcium intake and blood pressure. The relationship was strongest for Black men. Such observational studies does not establish causation. Researchers therefore designed a randomized comparative experiment. Okay, so experiment, the wheel should already be turning about the randomness and your 10% condition, and then in your conclusion, being able to use the word cause. The subjects were 21 healthy Black men who volunteered. Okay, so I already know I'm not a random sample. But they were randomly assigned to 2 groups. 10 men received the calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic, which is the top number of your blood pressure, for a subject after 12 weeks in millimeters of mercury. an increase is going to appear as a negative number. So group number 1 had the calcium. Group number 2 had the placebo. So an increase in systolic top number. So we want it to increase appears as a negative number. Okay. Does the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? Carry out the appropriate test to support your answer. Ooh, interpret the p-value. Oh my. Okay, here we go. We are a 2-sample t-test for the difference of means. 2-sample. Now, don't get thrown off. You had a group of 21 subjects who volunteered. So it looks like there's 1 sample. But it was split into 2 separate groups. 10 of them got a calcium supplement and 11 of them got a placebo. So now I'm in 2 separate samples. So this is not a matched pairs, this is a 2-sample. If the 21 volunteers each received a placebo and the calcium supplement, then we would be a matched pairs. But it was divided into 2 groups. So it can be kind of tricky. Okay, so 2-sample t-test for difference of means. Mu sub 1 is the true, think about what you're measuring. So I am measuring the decrease in their blood pressure. So the true mean decrease in systolic blood pressure for all healthy black men, like the ones in this study, who take a calcium supplement. Mu sub 2 is the exact same thing, but who take a placebo. My null is that there is no difference. Now, my alternate is going to be mu sub 1 minus mu sub 2. So that's calcium minus placebo. And I'm looking for that to be a positive difference, because an increase appears as a negative number. So I'm expecting mu sub 1 to be bigger. And my alpha was a 0.05. Conditions, random. Yes, but not random assignment, not random sample. The subjects were randomly assigned to the treatments. Therefore, independent condition is not needed. Normal, CLT does not apply, so I type both of these into my L1 and the other one into my L2, and I do a box and whisker for each one individually. So you're going to go stat plot, go over to a box and whisker for L1, graph it, and then you're going to do the same thing, but switch it to L2 and graph it for both of them. No strong skewness, no outliers. Here we go. I also need some statistics about my samples. So I have my sample size, I have my mean and my standard deviation from the first sample, and I have my sample size and my mean and my standard deviation of the second sample. Now, notice that these are X bars and S's because this came from sample information. So I don't have anything about population data. All I know is that I want I'm trying to prove that there is either no difference or that the difference is positive. So my mu sub 1 minus mu sub 2 is just going to be 0. I don't know what mu sub 1 and mu sub 2 are. The other thing is I don't know what sigma is. I only know what S sub X is. So when I come here, notice that I have S's and not sigmas because I don't have sigmas. So again, don't memorize, just understand the information that you're given. So T equals, I got X bar sub 1 minus X bar sub 2 minus the mu's, and then I've got my square root with my S's and my N's on the bottom. There's my X bar sub 1 minus my X bar sub 2. There are my standard deviations. There are my two sample sizes. Okay, please pause this and type that in and make sure that you get the same test statistic that I did. Then I take that t value, I come over here, and I'm going to find my p-value. Degrees of freedom, I have two sample sizes, so I'm going to use the smaller one. So 10 minus 1, that's where I got the 9 from. And I got a p-value of 0.0716. Now, my alpha was 5%. So since our p-value is greater than the level of significance for this test, we failed to reject H sub O. This experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like these who take calcium than the placebo. Our data is not statistically significant. Now, that's an experiment conclusion, and so that second sentence about the evidence gets a little bit more tricky because you can only generalize this to men like these. Now, you can go into description as to what that is, or you can kind of use that to kind of blanket statement, but that needs to be in there. And then our data is not statistically significant. Now, I did want interpretation of a p-value. Assuming that your H sub O is true, so assuming that there is no difference, mu sub 1 minus mu sub 2 is 0, assuming that that is true, there is a 0.0716 probability of getting a difference in the mean blood pressure reduction, calcium minus placebo, of 5.273 or greater just by chance. Now, let's focus on where he came from. So he is the difference between those two numbers. 5 minus a negative 0.273. So practice that p-value statement because he's not going away. Okay? All right. So the last thing I want to talk about is just making sure that you can read and understand the difference between a one sample matched pairs and a two sample. So let's read A. To test the wear characteristics of two tire brands A and B, one brand A tire is mounted to one side of each car in the rear, while brand B tire is mounted on the other side. Which brand is determined by flipping a coin. Okay, so think about if you think that's a two sample or one sample matched pairs. Can listening to music while working increase productivity? 20 factory workers agreed to take part in a study to investigate this question. Researchers randomly assigned 10 workers to do a repetitive task while listening to music, and the other 10 workers to do a task in silence. So B, I think, is pretty obvious that it's a two sample. You have 20 factory workers, but they were separated into two groups. 10 workers did this particular task, and the other 10 workers did this particular task. They didn't switch. So my sample size is 10 for both. So that's a two sample. However, A is a one sample matched pairs. The match is the car. To test the wear characteristics of two tire brands, A and B, Brand A is mounted to one side of each car in the rear, and B is mounted to the other side, because tires are going to wear differently on different cars. Okay, you have a Honda Accord and I have a Ford F-150 Super Duty, I don't know, whatever. Our tires are going to wear differently. So it's matched through the type of vehicle. So that would be a one sample matched pairs. Okay, so I hope this was super easy. This was a lot of information, but because it's so similar to everything we've been doing, I figured you guys could handle intervals and tests all in one day for means. So just be careful and don't overlook interpreting that p-value. I know it's a pain in the butt, but it is something that you need to be comfortable with.